Stray voltage in home plumbing refers to small electrical currents flowing through water pipes that are not supposed to be there. These currents can come from several sources. Firstly, faulty electrical wiring inside the home. Secondly, grounding problems in the electrical system. And thirdly, electrical equipment connected to the plumbing, such as water heaters or sump pumps. Sometimes stray voltage originates from outside the home, from nearby power lines or buried electrical cables. When stray voltage flows through plumbing pipes, it can cause electrolysis, an electrochemical reaction. During electrolysis, the metal in the pipes, like copper or iron, reacts with the water, corroding the pipes. Bonding the water pipe to the electrical system's ground can make electrolysis worse because it gives stray voltage a way to enter the plumbing system. Installing a piece of plastic pipe where the water pipe enters the home is one solution. The plastic pipe acts as an insulator, blocking electrical conductivity between the water pipe and the grounded electrical system. This isolates the plumbing from the stray voltage and lowers the risk of electrolysis. Grounding well pipes to the electrical system has been a common way to provide a ground path for electrical equipment connected to the well. However, this practice can harm submersible pumps in the well due to stray voltage. Stray voltage can damage the insulation of the pump's electrical components, which leads to premature failure. The issue of stray voltage in home plumbing shows that improper grounding can cause electrolysis and damage mechanical components. Installing a plastic pipe to isolate the plumbing system from electrical ground can help, but it is important to consult licensed electricians and plumbing professionals to address stray voltage issues and ensure electrical safety. Electrical safety must be maintained when performing any electrical work. Be sure that the power is off and that you are working according to local and national electric codes. Working with a licensed electrician is also recommended. Electrical systems are typically grounded at the service entrance. This means that a grounding electrode conductor is connected to a grounding electrode, such as a ground rod or a metal water pipe that is in direct contact with the earth for at least 10 feet. The purpose of this grounding system is to provide a low impedance path for fault current to return to the source, which helps to trip a circuit breaker or fuse and clear the fault. This protects people and equipment from electrical shock and damage. Bonding is another important aspect of electrical safety. Bonding involves connecting all metal parts of an electrical system together, such as metal conduits, enclosures, and equipment frames. This creates an electrically continuous path that helps to ensure that all metal parts are at the same potential. This reduces the risk of electrical shock if someone comes into contact with a metal part that has become energized. The National Electrical Code, or NEC, provides detailed requirements for grounding and bonding. These requirements are designed to ensure that electrical systems are installed and maintained in a safe manner. It is important to follow the NEC requirements when working on electrical systems. According to the NEC, specifically Section 250.52, a metal underground water pipe is permitted as a grounding electrode if it is in direct contact with the earth for 10 feet or more. This connection must be made within 5 feet of the point where the water pipe enters the building. Additional electrodes must supplement the water pipe electrode. The NEC also addresses bonding requirements for metal water piping systems within a building. Section 250.104 states that metal water piping systems must be bonded to the service equipment enclosure, the grounded conductor at the service, the grounding electrode conductor, or to one or more grounding electrodes. The bonding conductor must be sized according to NEC Table 250.102 Kern. This bonding helps to ensure that the water piping system is at the same electrical potential as the electrical system, reducing the risk of electrical shock. The NEC also provides requirements for grounding and bonding of oil pumps and submersible pumps. Section 250.112 requires that metal well casings be bonded to the equipment grounding conductor of the pump circuit. This helps to ensure that the well casing is at the same electrical potential as the electrical system, reducing the risk of electrical shock. Stray voltage is a phenomenon where small voltage differences exist between conductive objects that should ideally be at the same potential. In the context of plumbing, stray voltage can occur due to various reasons, including faulty wiring, improper grounding, or inductive coupling from nearby electrical circuits. When stray voltage is present in plumbing systems, it can lead to electrolysis, a process where electrical current causes the corrosion of metal pipes. Electrolysis occurs when the stray voltage drives ions from the metal pipe into the surrounding water, resulting in the gradual erosion of the pipe material. This corrosion can weaken the pipes and eventually lead to leaks or failures. There are several methods to mitigate stray voltage and prevent electrolysis in plumbing systems. One common approach is to ensure proper grounding and bonding of all metal components in the plumbing system. This helps to equalize the electrical potential between different parts of the system and reduce the flow of stray current. Another method is to install dielectric unions or plastic fittings to electrically isolate different sections of the plumbing system. This breaks the conductive path and prevents stray current from flowing through the entire system. In some cases, it may be necessary to identify and correct the source of the stray voltage. This may involve inspecting the electrical wiring and grounding system to identify any faults or improper connections. It is important to note that addressing stray voltage issues requires a thorough understanding of both the electrical and plumbing systems. It is recommended to consult with qualified electricians and plumbers to properly diagnose and resolve stray voltage problems. According to the NEC, specifically Section 250.45, exposed metal parts that are likely to become energized must be connected together into the supply source in a manner that establishes an effective ground fault current path. This path must be permanent and continuous, have ample capacity to safely conduct any fault current likely to be imposed on it, and have sufficiently low impedance to facilitate the operation of the overcurrent devices in the circuit. The effective ground fault current path is essential for clearing ground faults and protecting people and equipment from electrical shock. When a ground fault occurs, the fault current flows through the ground fault current path back to the source. This high current causes the overcurrent device, such as the circuit breaker or fuse, to trip and interrupt the circuit. Without an effective ground fault current path, the fault current may not be high enough to trip the overcurrent device, which can result in a dangerous situation. The NEC provides specific requirements for establishing an effective ground fault current path. These requirements include the use of equipment grounding conductors, bonding jumpers, and proper connections. It is important to follow these requirements carefully to ensure that the electrical system is safe and reliable. The equipment grounding conductor is a conductor that connects the non-current carrying metal parts of equipment to the grounding system. This conductor provides a lower impedance path for fault current to flow back to the source. The equipment grounding conductor must be sized according to NEC Table 250.122. Bonding jumpers are used to connect metal parts together to create an electrically continuous path. These jumpers must be sized according to NEC Table 250.102 cone. Proper connections are essential for ensuring that the ground fault current path is effective. All connections must be made using approved methods and materials. Loose or corroded connections can increase the impedance of the ground fault current path and reduce its effectiveness. In addition to the requirements for establishing an effective ground fault current path, the NEC also provides requirements for ground fault circuit interrupters, or GFCIs. GFCIs are devices that are designed to protect people from electrical shock by detecting small ground faults and interrupting the circuit. GFCIs are required in certain locations, such as bathrooms, kitchens, and outdoor areas. It is important to install and maintain GFCIs in accordance with the NEC requirements. Stray voltage can also be influenced by the type of soil surrounding underground utilities. Different soil types have varying levels of resistivity, which affects the flow of electrical current. Highly resistive soils, such as sandy or rocky soils, tend to impede the flow of current, while conductive soils, such as clay or loam, facilitate the flow of current. When underground utilities are buried in different soil types, stray voltage can occur due to the difference in soil resistivity. For example, if a metal water pipe is buried in conductive soil and is connected to an electrical system grounded in resistive soil, stray current may flow through the water pipe as it provides a low resistance path to ground. This stray current can cause corrosion of the water pipe and other nearby metal structures. To mitigate the effects of soil resistivity on stray voltage, it is important to consider the soil conditions when designing and installing underground utilities. One approach is to use sacrificial anodes, which are metal electrodes that are intentionally buried in the soil to provide a preferential path for corrosion. The sacrificial anodes corrode instead of the underground utilities, protecting them from stray current corrosion. Another approach is to use cathodic protection systems, which apply a small electrical current to the underground utilities to counteract the effects of stray voltage. These systems can be either impressed current systems, which use an external power source to supply the protective current, or galvanic systems, which use sacrificial anodes to generate the protective current. In addition to soil resistivity, the presence of moisture in the soil can also affect stray voltage. Moisture increases the conductivity of the soil, which can enhance the flow of stray current. Therefore, it is important to consider the moisture content of the soil when assessing stray voltage risks. In areas with high moisture levels, it may be necessary to implement additional mitigation measures to protect underground utilities from stray current corrosion. These measures may include the use of coatings, wraps, or other protective barriers to isolate the utilities from the surrounding soil. According to the NEC, specifically Section 250.166, underground metal gas piping systems must be isolated from electrical systems and equipment. This isolation helps to prevent stray voltage from flowing through the gas piping system, which can cause corrosion and other problems. The NEC requires that a dielectric fitting or union be installed in the gas piping system at the point where it enters the building. This fitting or union must be capable of withstanding the voltage and current that may be present in the electrical system. In addition to the dielectric fitting or union, the NEC also requires that the gas piping system be bonded to the electrical grounding system. This bonding helps to ensure that the gas piping system is at the same electrical potential as the electrical system, reducing the risk of electrical shock. The bonding conductor must be sized according to NEC Table 250.102 cone. The NEC also provides requirements for grounding and bonding of electrical equipment located near gas piping systems. Section 500.8F requires that all electrical equipment located within 10 feet of a gas piping system be grounded in accordance with the NEC requirements. This grounding helps to prevent stray voltage from flowing through the gas piping system. It is important to follow the NEC requirements carefully when working with gas piping systems and electrical equipment. Failure to do so can result in dangerous situations. Stray voltage issues can be complex and may require the expertise of qualified professionals to diagnose and resolve. It is important to consult with licensed electricians and plumbers to properly address stray voltage problems and ensure the safety of electrical and plumbing systems. The information provided here is for general educational purposes only and should not be considered as a substitute for professional advice. The NEC is a comprehensive code that covers a wide range of electrical safety topics. It is important to consult the NEC directly for specific requirements and guidelines. Always follow the NEC and local codes when working on electrical systems. Safety is paramount when working with electricity. Always take precautions to protect yourself from electrical shock and other hazards. The information is not exhaustive and does not cover all possible scenarios. It is important to consult with qualified professionals for specific advice and guidance.